Hi, I'm Holden, one member of Team Textrix, and we built Retrospect as our capstone project. The agenda for today: first, I'll introduce Retrospect, why we built it, how you can use it, and what's the ideal use case. Next, Earl will talk about existing solutions in this space, and then how Retrospect works in more detail. After that, Nicole will talk about the design challenges associated with Retrospect and how we handled them. After that, I'll walk through two more demos showcasing Retrospect in slightly different use cases. And then finally, Svetlana will talk about the installation and spin-up process for Retrospect. So as part of the introduction, what is Retrospect? So Retrospect is a full stack tracing tool for debugging small, distributed or monolithic applications. Retrospect records browser events and backend request data and puts them into a single user interface so that developers can debug their applications with service traces and session replay. Now, what does it look like to debug with Retrospect? Imagine that you have an application, an e-commerce website, in this case, Bob's Shop. You can see that it is a microservices architecture with an authenticate service, inventory, payment, and shipping service. Notice also in the right that Retrospect is connected both to the client and to the backend. Now, sometimes your application breaks. In this case, the user attempted to check out, but they were unable to, and they file a complaint with the owner, Bob. Now, before we go into the debugging step, let's see what Bob's Shop looks like. So this is a recording of the user interface. We can see the user adding apples to the cart, cherries to the cart, and then checking out. We can see them adding their information, as well as the items that they added on the right. Notice or note the email, ivan@gmail.com. That will be important when we walk through the debugging later in this presentation. Now, the payment method information will not be recorded by Retrospect. Bob is able to add some special class names to the HTML so that credit card number, expiration, and CVV are not recorded. Also, they click the submit button multiple times without success. So now what does it look like to debug here? And Bob has two pieces of information when he's debugging. He knows the user's email, ivan@gmail.com, and he knows that the checkout failed. That's it. So how does he start? The first thing he'll do is search the backend data for the user's email. He looks for ivan@gmail.com. And the Retrospect user interface makes it really easy to search through this backend request data. He can then sort by the date of span to get the most recent data because he knows the request failed recently. And now we can look at the span details card. He just clicks on a row and you get this more detailed view. Now there's a couple of very interesting pieces of information here. First, the waterfall chart at the top looks wrong to Bob. You may not understand it, but Bob recognizes that this looks too short. Normally, the checkout process has 5 bars. This only has 3, which tells Bob that the checkout process got interrupted somewhere on the back end. Second, a little bit lower, Bob can see that the status code returned to the user was a 400, confirming that an error occurred. And then finally, in the request data portion, he can see that the customer email was ivan@gmail.com. Unfortunately, this is not enough to tell him what exactly went wrong, so he clicks on the chapter ID. We haven't explained chapters yet, but think of them as a combination of the front-end browser events and the back-end data associated with a particular transaction. And again, Bob remembers that the waterfall chart looked wrong, or looked too short, so he can click on that last bar in the chart to get more information about the back-end request. In this case, he opens up the span tags, and he can see that the last request sent was to the inventory service, to the inventory not available endpoint, and that it returned a 200. Now this tells Bob a couple things. 1, the checkout process ended after inventory, but he's not sure why. 2, it sent a 200. So it's not that the inventory service was broken, it's that something else happened prior to that inventory service being hit that caused the checkout process to end prematurely. Now at this point, Bob is stuck. Nothing on his backend tells him what the answer is, why this process stopped. He needs more information about what the user did. Unfortunately, when he reaches out to the user, they're not responsive. As you may know, the user likely went to another website and has already purchased their products and is not interested in helping Bob debug his own website. If this were a normal tracing tool, Bob would be stuck. But Retrospect is not a normal tracing tool. Bob can click on the session ID and he can see an exact reproduction of what happened in the browser prior to the error. He can see that Ivan added apples and cherries into the cart and then what the checkout process looked like. This is extremely valuable for Bob because he can confirm a couple things. One, that Ivan was using correct credentials when he went to check out, and two, he can confirm what the user did on the front end that may have triggered an error. And so Bob will then look more closely at that session replay when he's trying to debug. So remember, Bob has two pieces of information when he's debugging. One, the inventory service was the last service that got hit on his backend. Two, he knows that the user was trying to buy cherries and apples. Those are probably connected. And so when he looks at that session replay more closely, he can see that something impossible happened. You may notice it. They tried to add cherries, which there are 0 left in stock, into the cart. Not only they tried, they succeeded. So no wonder that when they attempted to check out, something broke. They're not available. And this tells Bob that something has gone wrong in his front-end code and maybe his back-end code. Those products shouldn't even be visible on his website, let alone be able to be added to the cart. And so this doesn't tell Bob exactly what line of code he needs to change, but it does give Bob a useful starting point when he begins to debug. This combination of front-end and back-end behavior that produces an emergent bug would not be solved with normal tracing solutions. So what would it look like if Bob tried to debug without Retrospect? So you have the same application with a microservices architecture. You have that same error when the user tries to check out, but now Bob doesn't have Retrospect. He can't just easily search the backend request data to find a request with ivan@gmail.com. He can't look at the session replay. So what does he do? Well, first, he has to check each of his services. He might check the shipping service, check the logs. Now, these are not easy to read, and their quality is entirely determined by the person who set them up. So if Bob can't find an answer, he's not certain that there isn't an answer there. He just doesn't know. And so he checks the next service, authenticate, checks the logs, still no answer. The payment service, no. The inventory service, maybe, but there's no confirmation. Like we saw in the Retrospect UI, the inventory service didn't return a 400 or 500 response. It returned a 200 because it was a legitimate request to the inventory not available endpoint. So nothing in the inventory logs tells him what the error was. We know that the error was a combination of front-end and back-end behavior, but Bob can't tell that. Instead, Bob has to reach out to the user, and they don't respond. Because Bob doesn't have session replay, he relies on the user being willing to talk to him and what their memory was of the transaction. Do you think the user can remember that cherries were out of stock when they went to add them to the cart? Probably not. And so why was Retrospect able to help him here? And that's because Retrospect is an observability tool for front-end and back-end recordings. We not only capture the back-end tracing data, but we also capture that browser activity. This reduces the amount of time Bob spent looking at logs because he doesn't have to check into each one of his services. He can just query in the Retrospect user interface. It also makes Bob less dependent on the customer because he doesn't need a back and forth with the user about what they did. He can just use the session replay. Now, we said Retrospect is an observability tool, but what is observability? You're probably familiar with 2 of the 3 pillars. Metrics are numeric values over time, things like status code frequency, average time to response. These could tell you if you have a problem by illustrating some irregular patterns in the data. Also logs, these are information with a timestamp, usually some contextual data. These can tell you what the problem is, which line of code threw an exception, but you have to find it first. So why did we focus on tracing? And that's because metrics and logs are insufficient in modern distributed application. You need tracing to tell you where to look before you can use something like logging. Now, to make this more clear, we can use the analogy of the game Telephone. You may have played it before. Debugging Telephone and debugging distributed backend architectures are very similar because they're both black boxes. When you put a request into a microservice architecture or you start a game of Telephone, you're sending a request or a phrase through a series of people, a series of microservices, and then you get the output, which often has distortions introduced, but you're not sure where or why. Now, in the real world, when you're debugging Telephone, you can ask each person in line, what did you say at this time? What did you say here? What did you say here? But when you're debugging microservices, it's not as easy. The customer often doesn't remember exactly what they said, and they don't know exactly what they received. And your microservices are very forgetful. They can't remember all of their responses to particular initial requests. And so that's where Retrospect comes in. Retrospect is the equivalent of handing that first person a sheet of paper that says, write down your name and write down what you said, and then pass that paper on. So by the time it reaches the end, if a distortion has been introduced, you can look at that sheet of paper, check the list of services and what they said, and find exactly where the transmission failed. To extend this analogy, logging would be the equivalent of giving each person their own separate sheet of paper and having them write down everything that they said. Now, this doesn't solve the problem though, because if a distortion gets introduced, you don't know where it got introduced. You still have to talk to every single person and read their entire paper because those papers don't get passed on like they would in tracing. And so what kind of questions can our retrospect application answer? It could tell you which service was down during the checkout process. Or in this case, it could tell you at which point did the process stop, like it stopped in the inventory service for Ivan. It could also say which account was a customer logged into when some event occurred. For example, Bob could confirm that Ivan Jones was using the correct credentials when they were checking out. It could also tell you which service took the longest to respond. We'll show you a demo later that illustrates this more clearly. Now, questions we don't answer. We can't tell you which line of code generated an exception inside of a service. That would be something like logging. We also can't tell you which services on average are the slowest. That would be a question for metrics. We can only tell you which services were slow for a specific series of requests. Now, the telephone analogy makes it clear in the real world what tracing looks like, but what does it look like with machines? Here's a service diagram for Bob's application. You can see the client connects to the API service, and then that connects to authenticate inventory payment and shipping services. The service trace is the waterfall chart that we looked at previously in the Retrospect UI. You can see that the first part is the API service, then authenticate inventory payment and shipping services. This reflects the order in which services need to be called. First, authenticate, then inventory, payment, and shipping. Remember that the checkout process got stopped at inventory for Ivan, so we didn't see the payment and shipping services. When we put these two together, you can see the relationship between tracing and the diagram. The service trace looks like the diagram spread across time. Now let's introduce some vocabulary that we'll be using a lot later. So a span is a single operation within a trace. In this case, you can see the arrow is pointing at the authenticate span, after which is the inventory span, payment span, shipping span. This tells you where the request went, what data it held, and how long it took by the length of the span. The root span is the first span. It's the parent of all these child spans. Notice that the API span cannot finish until all of its child spans, especially the shipping span, have finished. This is the first request to hit your architecture. And then the trace, this is the combination of a root span and all of its child spans. It's the complete path of a single request. This is the waterfall chart that we saw in the span details card. Now, I'll turn it over to Earl to talk about what observability tools Bob should use.
Thank you, Holden. So, how can Bob achieve a sufficient level of observability for this use case using existing solutions? Let's have a look at some of his options. Now, one avenue for Bob is to go with an enterprise solution. SaaS vendors such as Sentry, Datadog, and New Relic would provide a way to see backend traces in the context of front-end events as demonstrated. These enterprise solutions offer not only observability for traces, but also logs and metrics, making them feature-rich. However, the ease of outsourcing observability to a SaaS vendor comes at the cost of lack of data ownership and recurring fees. In the case of a small company like Bob's, where capital may be low, it may be better to allocate the money for those fees to other expenses and instead use an open source solution that provides just essential features for debugging a small microservice-based application. Another option for Bob is to go with a DIY solution. Bob can use open source solutions dedicated to recording front-end events and backend traces. The most prominent open source solutions for recording these include OpenTelemetry for the backend traces and RRWeb for the front-end events. However, Bob would have to spend time learning how to use these open source solutions properly. Moreover, they do not integrate with each other out of the box. So Bob would have to find a way to customize RRWeb and OpenTelemetry such that the front-end events will be connected to the backend traces they correspond to. The time and energy Bob would expend to get a DIY solution set up would be better spent on the core functionality of his application. Now, what if there was a solution that offered the ease of deployment offered by enterprise while also providing the benefits of DIY. This is where Retrospect fits. Retrospect connects the related events and traces of the instrumented application out of the box, thanks to its ready-made pipeline. The user will retain data ownership as the database instance is deployed in the environment of their choosing. And it comes with a simple yet powerful UI for debugging small microservice-based applications. While it may not be feature-rich enough to give you real-time performance analytics or, say, the trend of your website's conversion rates, it will provide you with the context necessary to figure out what services to investigate given an error. Now let's see how Retrospect works. In short, Retrospect is a full-stack tracing tool for small microservice-based applications. It is comprised of 6 pieces that work together to collect, connect, and select backend traces and front-end events. Let's take a closer look at the different architectural components. First is the collect group. The client and server agents are responsible for collecting the data from the instrumented application. For the client agent, we use the open source web session recording library RRWeb with modifications to attach metadata onto requests that connect the recorded events to the relevant backend traces. For the server agent, we use the open source observability framework OpenTelemetry. Similar to the client agent, we modified OpenTelemetry to attach metadata that would allow us to connect these backend traces to the relevant front-end events. Now, here's a closer look at the agents at work in Bob's application. When a user visits Bob's app, the Retrospect client agent takes full DOM snapshots and listens for DOM mutation events and mouse clicks. It sends these dehydrated events to the Retrospect API after attaching metadata required for connecting them to their respective backend traces recorded by the Retrospect server agent. When the user triggers an HTTP request to Bob's backend, the Retrospect server agent creates the span that will be passed along the microservices involved in the HTTP request. This span is the pencil and paper from the telephone analogy, and our Retrospect middleware attaches the metadata required for connecting each span to the user session that triggered their HTTP requests before they are sent to the Retrospect API. Next is the connect group. The 3 pieces for connect are the API server, an instance of a Cassandra database, and a server containing scheduled data maintenance tasks. The API server receives the data from the agents and transforms the contents for easier querying before sending it to Cassandra. It also serves data to the UI by making CQL queries to Cassandra. Cassandra is our data store of choice. This design decision will be covered in greater detail later, but in short, we chose Cassandra due to the high volume of events Retrospect would consume from the instrumented application. The scheduled tasks server contains cron jobs that maintain the database by purging data older than a set number of days, configurable by Bob. It also solves a technical challenge we faced with using the current implementation of OpenTelemetry, as the metadata isn't propagated properly to database spans. The API places these unidentified database spans in a buffer within Cassandra, where they'll stay until their requisite metadata is attached to them by the cron job. The last piece of Retrospect is our UI, which allows for the selection of specific events and traces. We designed the UI to have a good balance between simplicity and power, while also thinking about the user experience. Our design decisions for our UI were driven by us ourselves developing Bob's microservice-based application, instrumenting it with Retrospect, and inducing errors in Bob's different microservices. We also consulted working developers to make sure our UI had the features they thought were necessary for our use case. The result was a UI that was quite fun to use internally. Now, it may not have all the bells and whistles of the bigger enterprise solutions, but we aren't aiming to be a complete 3 pillars observability solution like they are. Our focus is on the traces through your architecture, to give your microservices the paper and pencil in their game of telephone. Now I'll hand it over to Nicole for the design challenges.
Okay, thank you, Earl. So next we're going to talk about how did we build Retrospect, starting from the design choice and starting from the project choice and going through how did we come to the final project that is Retrospect during all three steps of the way. So first we are going to talk about connecting events with traces. Then we're going to talk about how we store data, and finally we'll talk about some choices about the UI. So first, we talked about OpenTelemetry and our web and how they do really well with the front end and the back end. Specifically, they are highly customizable. They're feature rich. OpenTelemetry focuses on the back end and our web on the front end, but they don't actually talk to each other natively. They focus on their own domains, but they don't have adapters to connect them to outside technologies. So as we're going forward, let's just remind, so traces refer to the backend. So traces refer to the backend conversations between services and architectures, and events are fired by the user. So with OpenTelemetry, our web, we're able to record traces and events. And first thing we're going to do is we're just going to store that somewhere. So let's take a look at that. Next, yeah, here. So we have traces on one side, we have events on the other, and these are clustered into two different tables. Great. This is a great first step, but we don't have any way to connect them. So first thing we did, we decided to borrow an idea from browser cookies, where we wanted to create and pass along a session ID. Now, there's not any way to do that out of the box. OpenTel and our web are not designed for this. They're not designed to take extra baggage, as we started calling it, in the form of additional headers and content. So we had to build a custom span processor that handles this. So on the front end, this plays out with, we built a wrapper that intercepts and appends our own metadata onto events that are being sent out. On the back end, through experimentation, we figured out how to forward this metadata along with all of the traces, or with all of the spans within it. So the first thing we did once we had this technology was we added session IDs. We generate a UUID on the client, and that gets sent on to all of the, it gets sent on with all of the events and with all of the traces. So let's take a look at what that shows. Huzzah, we have traces and events, and they're in a box now. We have a session. And next, we'll even show how this is useful, because we have multiple sessions. My session is different from your session. If I go to Bob's site 3 times, I will have 3 different sessions. This is great. However, this isn't, even though this is still very useful to Bob, and while Bob would be able to find what he's looking for, it's not useful enough. In fact, as we start looking at what the data looks like next, here we see sessions are good for the big picture, but they're too broad for debugging. Here we have 4 traces in a 6-second session, but this isn't immediately useful. And if we were to impose all of the events onto this graph, so this is a waterfall chart. It shows the different traces. It doesn't show all of the user events. If we were to impose all of the user events on here, we would maybe be able to guess which events led to which, but that would require some special inference on the user side, and that's not immediately useful. So how can we organize them? So we came up with chapters. Chapters are similar to mini sessions. It connects one single trace and all of the spans that are composed within that trace, one single trace with all of the events that lead up to it. So a session is large and will have 1 or more chapters, but a chapter is a specific set of events that lead up to a single trace. So whenever the client sends a new request to the server that would start a trace, it creates a new chapter ID. And with that, we're able to now have 2 forms of identification. And so next, we're going to show what that looks like. Now we have the data is organized. So these events lead to this trace. These events lead to that trace. These are organized into chapters. So it's all neat and orderly. And next, when we focus on a single chapter, we're able to see what does that look like. So here we have a chapter and all of the spans that are within that. We have the waterfall chart. It has the durations in a nice graph format. We have the spans on one side that were related to it, as well as all of the events that are specific to what led up to that chapter. So next, we have figured out how we're going to organize and collect the data. Now we have to talk about how we're going to store it. So what are our data requirements? So the big problem here is we have a lot of data, high write volume. Our users are going to be creating, well, the customers of Bob's app are going to be creating a lot of user events. This is a ton of writing. Hopefully it's not going to be so much reading. So we need a database with a high emphasis on write speed, but not as much on read speed. However, reading will still be kind of involved. So we can't just not have that. We can't just dump it all. We also have structured data. Our data fits a relationship-like schema. It's not a key value store. And while we did use MongoDB early on for just storing data, document stores aren't going to work nicely with the kinds of queries that we're going to be running. And then lastly, it needs to scale really well. Every single user is generating a lot of traffic. As Bob's app grows, as he adds more web servers, he's going to also need to add more database clusters to handle this load. So there needs to be something that can scale really, really well with that. So we had a few different approaches that we investigated, and our solution next is to use Cassandra. Cassandra offers us several benefits. It offers us the write speeds that are afforded by a NoSQL database. There's no cross-table operations. However, even though there are no cross-table operations, it's not a document store. It stores the data in a tabulated format. It stores the data in a row column format that is very similar to Postgres or other SQL environments. In fact, it's a SQL-like NoSQL database solution. It also scales linearly. Bob can add new nodes to the cluster very easily. He can just, if he needs 2 times the amount of traffic, he can just add twice the amount of nodes, or even he just doubles the amount of nodes and he has double the amount of performance. It is actually that easy. Whereas with traditional relational database schemas, that's difficult. That's when you get into database sharding. That's when you get into partition schemes. A lot of that is handled for you with Cassandra. When you set up the schema, you set partition keys, and it's its own thing. But then day-to-day performance, Bob doesn't have to worry about that. Bob just adds new nodes onto the cluster. So then lastly, we are going to talk about the UI optimization. We want our application to be very useful to Bob. So next, we'll talk about this. We want this to be very useful to Bob. We don't want it cluttered with unnecessary features. We want it easy to search. We want simple, succinct, and useful. This means that everything has a purpose. Everything has a place. Bob needs to be able to search. We're not just exposing a database console. We're giving Bob the tools he needs to search through the data. This is really important. All of the traces, all of the spans, sessions, chapters, these are all identified by very long, incomprehensible strings. Even though he's looking for ivan@gmail.com, that data is stored nested within a data structure that is stored within several layers of identifying strings. And those aren't easy to write queries for manually. We don't want Bob to have to deal with that. We don't want him to have to learn a new query language. He needs to be able to search very easily. And so we offer that. And here we just have an example. So when Bob is looking at the spans, we have filtering options, we have the exporting options. If he clicks on a span, it shows the span details over on the side. And that offers top-down view, it offers details. And if that's not enough, he can click on the chapter ID or the session ID, depending on whether he's looking big picture or smaller picture. And this lets him navigate to the problem he's looking for very, very quickly. Now, we're actually going to talk about this a little bit more. In order to do that, we're going to have Holden give us a demo.
Thanks, Nicole. Yeah, as I mentioned previously, there's 2 more demonstrations of how you would use Retrospect for slightly different use cases. The first one, a service is down. The initial demo was a front-end error, possibly a back-end error. This one of the microservices is unavailable. So we can see the customer going to check out. Again, note the email, shipley@gmail.com. We're going to reference that later. And as Earl mentioned, we're not recording with a video. We use dehydrated DOM snapshots. You can see the checkout failed. So now what does Bob do? Bob goes to span search. And instead of searching by request data, Bob can also search by the date of the span. He knows that the checkout failed recently, so he could check for, I want the most recent spans that are after 3 o'clock on July 30th, when he received the complaint. You can sort by the date of span, and because Retrospect also shows you the status codes, he can then look for a 400 or 500 level status code, which he expects will be the cause of the failed checkout. And again, we can confirm we're looking at the right email with shipley@gmail.com. So next, Bob clicks the chapter ID, and we can see that same waterfall chart. We can also see the list of spans associated with that chapter and open the one that has that 503. Now, Bob knows it's probably the last span, so he clicks on that last one, and we can look at it more closely. We can see that it returned a 503. The service was unavailable, and we can confirm it by looking at the span tags. This lets Bob know why did that checkout process fail. It's because one of his services was unavailable. This would be extremely hard to debug without something like Retrospect, because if the service comes back up in between the time of the complaint and when Bob starts to debug, there would be no record of the service having gone down. You wouldn't see that failed request. The next situation, the payment service is delayed. We mentioned this earlier, that waterfall chart can tell you how long did a service take to complete. In this case, someone named Dale@gmail.com is trying to check out. Note that we've sped up the GIF, so it'll only seem to be a 2-second delay, but really it's a 5-second delay. This could also be 10 seconds, 30 seconds, etc. Now, what does Bob do? He can search the request data for that email. In this case, all he needs is Dale. And you can see immediately on the chart that something looks wrong. It looks a little bit too long. And so Bob goes into the chapter ID view, which we see here, and it should be immediately obvious which service is causing the problem. It's that payment service. So when we restart the GIF, you'll be able to see Bob sees the waterfall chart, clicks the extra long span, and when you look at it, you can see the time duration was 5 seconds, exactly as we said. And if you go into the span tags, you can see more information like which service it was sent to, giving Bob a good place to start debugging. Now, next, I'll turn it over to Svetlana to talk about installation.
Awesome, thank you. All right, let's start with the client side first. So what Bob has to do to instrument the front end is to install our client agent with npm, and he only has to do that on the client. The second step is to update the config file. Here, he will have to update the endpoint to point to the API that Earl was talking about. This will send the front end data to the API. Step 3 is to update the index.js file. Here, Bob will have to import the recorder from the client agent package and start it. To add the client agent to the server side, Bob will have to do 4 steps. Step 1 is to install the server agent on the backend to capture traces. Step 2 is to update the config file here too. Here he will have to update the service name. Then he will have to update the DB options to true if he's going to use a specific database option. And then step 3 is to update the endpoint to allow spans to be sent to our API that he did for the client agent as well. Step 3 is to update the index.js file. Here, Bob will have to import the server agent into his startup file and use it as a middleware. And then step 4, Bob will have to update the start script of his server to start the tracing file before starting his server startup file. So this would be his index.js file. The last thing Bob has to do to deploy our tool is he would have to use Docker. To do that, there are 2 easy steps. First, you will have to download the Docker Compose file and just run Docker Compose up. And then he will be able to see our UI on port 3200. And that's pretty much it. This takes us to the end of our section, and we will take your questions now.
Okay, we already have one question, so I'm going to read it. So capturing every DOM change for each of your users sounds like a very high volume data transmission exercise. And you explained the storage benefits of Cassandra in dealing with high volumes data quite well. How does Retrospect think about minimizing the amount of data sent over the wire, as well as keeping request response cycles as short as possible?
Yeah, I can take that. If no one else wants to, we approach it from a couple levels. The first is that, just to be clear, I think you understand this, but we don't do a full DOM snapshot every time there's a change to the DOM. There are full DOM snapshots at increments, but in between then, it only registers individual changes, like small changes to the DOM, so that when we build the session replay, it has those snapshots and then it applies the changes in sequence before you get to the next snapshot. That helps significantly reduce the size of the data that we send. Second, you can configure the recording settings so that you don't record the most active type of events. For example, you might have noticed in the session replay, we don't record all the mouse movement. Those are especially egregious in terms of generating lots and lots of events. So by default, we configure our web to not record them. And the third one is the size of the data, and that's being sent is actually very small. We have some statistics that we generated for testing this. And in terms of consuming CPU time, the self time of the longest session recording operation is about 4 milliseconds, which is below the human noticeable range. And our effect on the Lighthouse score for Bob's application was only a reduction of 1 point. I hope that answers your question.
Okay, awesome. So Elizabeth said, excellent job, Team Retrospect. And Lena said, amazing presentation. If you had more time, what kind of work would you like to implement?
Oh yeah, go for it, Svetlana.
I was gonna mention one piece. So I believe briefly mentioned it. So we would like to give Bob the option to show him the specific line of code that is throwing this kind of error. So we do want to add logs in the future.
Okay, Nicholas says, great answer, thanks. Glad to see some benchmarking. And then Mark asks, why Cassandra over Mongo?
Sure, and so I'm happy to talk about that. So Mongo offers great for document writing. However, we want to query data. Our data fits a very relationship-like schema because every event is going to have a chapter ID and a session ID. Every span is going to have it's probably going to have a parent span ID. It's also going to have a chapter ID and a session ID. We want to query based on those. And with the amount of rows, with the amount of data that we're going to be storing, with a document store, we would have to search through the kinds of queries we'd have to go through would not be desirable. We want to be able to write a query like select from this where the ID is equal to an ID that we provide. And it's having a relational like data structure helps us with that. I hope that answers the question.
Okay, Laura asks, what was the most challenging part of the project?
Oh man, one of the hardest things that wasn't coding related was deciding where to stop, because it felt like there was always more and more interesting ways you could use session replay, or more and more advanced ways to apply that backend tracing, that auto instrumentation, and being able to say like, no, we can't add any more features. That was definitely difficult.
Okay, it looks like we don't have any more questions. So anyone? Oh, so yeah, we do have actually. So the first question is, how did you do the screen recordings?
Yeah, so we used a session recorder that uses the mutation observer API in the browser that records every change to the DOM. So it creates basically a buffer of events that have changed what the user sees in the browser, and then it emits them periodically, which we then export to our database. And then later, when we're trying to provide the session replay, we collect those events, that list of changes with the snapshots of the DOM, and then we send them into a special replayer object. We didn't build the replayer object, just to be clear, that takes those and recreates what the DOM looks like. The way it's phrased is dehydrating the DOM, reducing it to text, and then rehydrating it, basically reapplying the HTML or the CSS processing so it looks like the user interface.
Okay, so next question. What process did you use as you built the project?
I can talk about that. We took an agile approach. We used a pivotal tracker that we stayed on track of. This helped each of us because for most of the project, we separated things into, I'm going to work on this part, you work on this part, you work on this part. And sometimes this would overlap greatly. So keeping things as far as, so this story blocks this story, that was helpful. And it also helped keep each of us have a list of what are some next things that we can do, what are some next concrete goals that we can work on to help further the retrospect project.
Yeah, I think the that Trello clone project was incalculably beneficial in terms of teaching us how to create concrete stories that let us work more effectively.
Okay, so this is a question for each one of you. So what was the most rewarding part of working on this project?
I would say for me, the best part was sharing it with different people and seeing how how they think of it and the kind of feedback that they share with us.
I definitely enjoyed working with all the data, working with the API server. I got to write a highly performant API server with Golang, and I found a lot of personal appreciation for that. And I also got to work on putting the Cassandra cluster together. That was just a lot of fun for me. I really enjoyed this work.
For me, I'd say my favorite part was working alongside working developers to try to get the correct features in, and also working with the UI. You can see your work immediately, whereas for backend work, it's not as apparent. So yeah, working with optimizing the UI's features was very rewarding.
Yeah, I definitely agree with all of those. I think my favorite part is like getting to work with a small team on a hard problem. I don't know, I played a lot of team sports and I was at a small startup before this, so it feels really good to be like, we have this maybe impossible problem. Like we don't even know if we can do this, but there's 4 people putting their heads together trying to figure it out. And if you don't know how to do it, you know there's someone else who is also really, really good, like trying to solve it at the same time. And it's so satisfying to work through.
Very nice. So Owen says, really impressive work, guys. It's easy to see how useful a tool like Retrospect could be, especially for complex microservice apps. So a question, client-side input can contain sensitive data like passwords, credit card info, and so on. Are there any measures you built into Retrospect to secure sensitive user data?
Yeah, I could take this one. So we used our web for recording the session data. And RR Web offers a class you can add to inputs or elements in your HTML that would essentially block it from being recorded. As you saw from the session recording of Ivan Jones's session, his credit card info, the input boxes were grayed out. So someone like Bob can add those classes to his HTML elements to block them from being recorded.
Awesome work once again.
Yeah, thank you
Thank
so
you.
much, everybody, for coming.
Thank you for coming.